Okay, so this question, we've got a block that's held against a compressed spring on an inclined slope. At time t1 the block's released from rest. T2 the block reaches the equilibrium position of the spring, that's the E here in the diagram. T3 the block reaches the rough patch, so I'm going to assume the other stuff is frictionless. On the inclined slope, and at time t4 after passing across the rough patch the block comes to rest. Over the interval from t1 to t2 is the magnitude of the change in the spring potential energy greater than, less than, or equal to the change in gravitational potential energy of the block Earth system. It's a good question. So looking at the change in the spring potential from T1 to T2. So T2 is when the block reaches the equilibrium position of the spring. And you can think of that whether it's before or after. So you can do this from a couple of different angles in terms of what system you want to pick. So I could consider, I'll do this in two different ways. So thinking about the system of the spring block Earth. So I'm going to group everything in here. So since the Earth is in the system, there's no external gravitational force. The spring is in the system, so the internal spring force is also internal. Now there is a force by the ramp, but it's always perpendicular to the block. So the ramp doesn't do any work on the block during the T1 or T2 interval. There's also a force by the sort of pivot point here, or like the attachment point, that also does no work. So there's no work done choosing a system in which there's no work done. So the net external work on the SBE system is 0, which means that the delta E of the SBE system, don't need that, is also 0. So there's no net work during, again, from T1 to T2. So what is the delta E of the SBE system? So I know the delta E of the SBE system is the delta U of the spring plus delta U grav of the block on the Earth plus delta K of the block. And you could ask yourself, how do these quantities change over this interval? So I can see here the delta U of the spring is negative. It's going from compressed to not compressed, so since it's transferring energy into two other forms of energy. So it's raising the block, the block has been raised above the Earth, so there's an increase in delta UG. There's also an increase in delta KB, because the block is going to be, the block does move eventually past equilibrium. Again, I'll again stay on the updated version that the block is only held against the spring, it's not attached to the spring. So once the spring gets to equilibrium position, the block keeps going, so I know the block has an increase in kinetic energy. So that would tell me that the delta US is the sum of these two. Since the decrease in the potential energy of the spring goes into increase in the gravitational potential plus the kinetic energy, which makes the change in the spring potential energy, the magnitude of that change, greater than that of the change in the gravitational potential, because this is all equal to 0. So the delta US is equal to negative delta UG minus delta KB. So in a sense it's equal, and both these are both positive, so sort of a minus positive number minus some other positive number. So the delta US will definitely be negative, and it will be greater because it basically goes into the delta US goes, all of this energy is transferred into increasing two forms of energy, which means that it has to have a greater absolute value of change than the spring potential has to have a greater absolute value of change than the delta UG. So we can state that delta U spring magnitude is greater than delta UG. So that's one way of looking at the problem. You could also consider a system of the block alone. And this work net external on the block is only equal to delta K of the block. Again, before there's any friction forces on it. So there's two forces doing work on the block. There's work done by the spring and work done by the Earth. So work done by the spring plus work done by the earth equals delta K. I know the delta K of the block is positive during this interval. Work done by the earth is negative, and the work done by the spring is positive. So if the delta K of the block ends up being positive, and there's a positive work and a negative work, it means that the magnitude of the work spring has to be greater than the magnitude of the earth or gravitational work. And there is a direct connection, direct equality between the magnitude of the work done by the spring and delta U spring and the magnitude of the work done by the earth and delta U earth or delta U grav. So I can definitely state that delta U spring is larger than delta U grav because there is an equable term. Work done by a spring is negative delta U spring. Work done by gravity, so maybe E in gravity, maybe I can change these to G's, is equal to negative delta U grav. So if I can state that the work done by the spring is greater than the work done by the earth, I can definitely also state that the change in the spring potential energy, the magnitude of it, is greater than the change in the gravitational change, the absolute value of the change in the gravitational potential energy.